Okay, so I think it's time to start. All right, so today we're going to talk a little bit about well, these three topics. We're going to talk about linear approximations first. This is a very pragmatic thing to want to do using one variable and then many variable calculus. And then we'll talk about how we can find the tangent plane to a graph of a function of two variables when it exists. And then finally, we'll sort of end by talking about the existence of such things and when they may or may not exist, what it means to be differentiable. All right, so let's start with polynomial approximation. So polynomials, you guys know and love from one variable calculus, right? You have the monomials. So in one variable, we have monomials, 1, x squared, etc., right? And then each of these has a degree. So we get the degree 0, degree 1 terms, degree 2, and so on. Now, it's pretty straightforward in one variable because there's only one monomial in any given degree. In two variables, things get a little bit more dicey and more variables. But we saw last time a little bit of how we could assign a degree to a monomial with more than one variable. So here we had one, let's say x and y are our variables. And we could talk about x squared, xy, y squared, and then on and on. And here, our degree is the sum of the exponents of the variables. So here we have degree 0, but then in degree 1, we have two possibilities, x and y. And degree 2, we have 3. So this is the degree. And as you get larger, you get more possibilities. It's sort of linear with two variables, but when you get to 3 variables, it becomes quadratic, the growth of the number of monomials of a particular degree. Now, what we want to do is we want to take, in the real world, is we have a very complicated system with very complicated functions, too complicated, and we can't necessarily figure out what's going on with it. But what we can do is we can do basic arithmetic. So if we could estimate our functions using just these, linear or quadratic terms, then we'll get an easier way of computing things. That's one. And 2, we also get some qualitative information about the function. So, what we want to do in general is we start with our general function, f(x)(1) through xn. Let's say we're in n variables now. And we want to kind of expand it out like a Taylor series type expansion. Right, we'll get a constant term. Then we'll get some linear term. This is degree 1. This is a quadratic term. Degree 2. So sums of things like this, the quadratic, the linear sums of things like this. And then plus higher terms. This is sort of what we're going to do in this chapter without really thinking about it precisely this way. But today, we're going to focus on this bit. And of course, all of this is sensitive to a particular point. Okay, so it's sensitive to where we are. We can do different kinds of approximations at different points in the variables x1 through xn. All right, so let's give the definition of linearization of a function at a particular point AB. And then we'll work out a problem and soon see what this definition is telling us geometrically. All right, so let's let f be a function of two variables. Of xy with partial derivatives at AB. So in other words, the partial derivatives exist at AB, at a point AB. Then the linear approximation of f at AB is the following function. It's L, we'll denote L for linear, Lxy. We take the value, this is our constant, part of our approximation, the value of f at AB. And then we're going to take the partial of f with respect to x, evaluate that at AB. We said they exist, so we can do it. Multiply it times x minus a. And then the partial with respect to y at AB, multiply that by y minus b. This is what we call the linear approximation. All right. This gives us, so what you could think of is you can say, well, let's say I want to estimate, let's say I want to estimate my function f near my point AB. Well, the most naive estimate that you can do is you can say, well, it's just f of that point that I'm near to. So if I want to estimate the square root of, 4.1, I can say, well, 4.1 is close to 4, so it's close to 2. That's the constant estimate. That's just this. This term gives us a slightly better estimate. Okay. This does a little better than that constant bit. That's the idea in the cases where we're differentiable, which we'll talk about in a moment. All right, so let's do a problem though, just computing this and seeing how it's used. So let's approximate the following value. Square root of 2e to the x plus 2e to the minus y. Oops, I had said minus y. I said x and y. I want 1/10. Where's my bad, guys? 1/10, negative 1/5. Okay, let's get an approximation of that. I don't know if that's legible. Let me see if I can write it slightly more clearly. All right, so this is the problem. We've got an actual number here, and we want to get, of course, it's a hard-looking number, but we'd like to get a good estimate of it. So our solution is, well, first we're going to observe at this point 1/10 minus 1/5. Well, I'll do 1/5. This is not that important. You can do whatever you want. Observe that this point is close to the origin. Right? It's close to the origin, which I'll call AB. Okay, so let's take the function f of xy and look at the square root of 2 times e to the x plus 2 times e to the minus y. And so this is a function whose partial derivatives exist here. Or, well, we need these partial derivatives here. And so we can do an approximation, a linear approximation of this. So we're going to linearly approximate this at the point 0, 0. So let's take f of x. Now, I think I said it last time, when you're taking partial derivatives, what you don't want to do initially is this. You don't want to do that. Don't put in your values before you take your partial derivative. That's not going to work. So you want to first take a partial derivative, find the function, and then evaluate it at a point. So when we're looking for these values, first find the function partial derivatives, and then put in AB. All right, so for this, we just, again, we remember from last time, we need to treat y as a constant, and then just take the derivative with respect to x. If we do that, we'll get a 2 e to the x times, and we have to use the chain rule here. This is with using the chain rule. We get 1/2 2 e to the x plus 2 e to the minus y to the negative 1/2, just using a chain rule here. So we can cancel this. So if we evaluated the origin, which we want to do because our AB is the origin, we'll get e to the 0th power is 1, and we'll get 2 times e to the 0th plus 2 times e to the 0th is 4 minus 1/2. That's the square root of 4, 1 over the square root of 4, which is 1/2. Okay. Okay. So now we need to also do this for y. Not too hard. Again, we'll get 2 e to the minus y. Of course, I have to get a negative sign here because I've got a negative in the exponent. Oops, sorry. And then I get a 1/2, same kind of deal, e to the x plus 2 e to the minus y. And I get cancellation here. So if I evaluate at the origin, I'll get negative of what I had before, negative 1. It's working it through. So we've calculated the quantities we need. I guess the one thing we didn't calculate was actually the easiest thing, just calculate f at the point AB. So I missed that. Let me do that now. F at AB is just f at 0, 0, which is the square root of 4, which is 2. All right, so now I have all 3 things I need. I've calculated all 3 quantities I need. I need to get the value of f. I need to get the value of the partial derivative with respect to x of f, and the value of the partial derivative with respect to y of f, and then evaluate all of those at the point AB. Once I have them, I can put the I can form the function, which is the linear approximation. So L of xy in this case is going to be, well, I'll put it in f of 0, 0. I'm just going to put in the formula, and then we'll substitute the values. Again, a and b are both 0, so x minus a is just x. And y minus b is just y. And so this is going to give us 2 plus 1/2 x minus 1/2 y. And then if you put this in, now we're approximating this. So we're going to approximate this at the point here. So this is the xy that we're going to feed into our linear approximation. So L 1/10, 1/5. This is going to be equal to 2 plus 1/20 plus 1/10, which I have as 39/20, which is slightly better than 2. 1/20 better than 2. Hey, this is good percentage improvement. So this is actually, I mean, if you sort of follow this procedure to higher orders, this is how calculators calculate, right? They know the derivatives of a lot of these functions, and they're able to kind of just do basic arithmetic. Yes? I did, yes, thank you. It should be a minus here. Thank you. It's just me writing it down wrong, thank you. Other questions or comments? Dark in here for like reading. My handwriting is also really tiny. Excuses, excuses. All right. So this is linear approximation. It's not hard. It's just, you just have to compute these quantities and put the values in, and you're ready to go. But it's very, very useful, especially if if you want to know how computers actually compute. This is understanding how this works will help you quite a bit. All right. So now let's talk about tangent planes. So these are all, of course, very related. And I'm going to go back to one variable calc to remind ourselves what we did there. So in one variable calc, we had the following kind of picture. We had function f, and it was some nice smooth function, and we took a value c, and we found the value of c of f. So this whole thing will be y equals f of x, and then we tried to find the tangent line, right? This is like the first thing that people would do that you learn in calc, right? You learn that the derivative is the slope of the tangent line, and you want to get an equation for the tangent line. Now, why do you want an equation for the tangent line? Nobody knows, right? Well, of course, if you look at 99% of models in real world applications, they're linear. They have all these linear models. And the point is linear is really easy to compute and work with. And you can actually get solutions to problems with linear functions. So these linear approximations do appear everywhere. And the reason you want this tangent line is because it is the graph of the linear approximation to your function. So how do you get it? Well, you'll recall what you get. You get that y is equal to the value of f at c plus f prime of c times x minus c. This is what you'll get. Do you guys remember that? Does this look familiar? As I said, this is the tangent line. This is the tangent line. The graph. This is the equation for the tangent line. So of course, now we're sophisticated people. Before we weren't. Now we are. Now you have a function of two variables. And we get some kind of horrible paraboloid. I don't know, whatever we got here. We've got some kind of two-dimensional function. And we take some point AB here on our plane. This is our XY plane. This is our Z. This whole thing here is our function, our graph of our function Z equals f of x. We look and see where that point goes, where AB goes to some point on this graph here. Oops. And we want to find a tangent plane. I want to find a tangent plane. Now, why did we spend all this time talking about what is the equation for a plane in 3 space, right? So that we could talk about things like tangent planes and linear approximations to functions of two variables. And of course, there's plenty of linear algebra for higher dimensions as well. So what you're after here is some kind of thing like this, some kind of tangent plane sitting on top of, just meeting that graph of your function right at that point. And the equation for this tangent plane equation is given by z equals, well, let's use this as a model. We take our value, f of AB, and we take our first order approximation. We have a single derivative. And indeed, you'll see what we're getting here is, of course, just the equation we had a second ago of the linear approximation. I'm going to have to give myself a little more room, though. So this is the equation for the tangent plane. If there is a tangent plane. If there is a tangent plane. This is assuming f is differentiable at AB, which we'll again discuss in a moment. Okay. Questions? Nothing so far. So I'm trying to tie together these notions, if they haven't already been really tied together for you: linear approximation and tangent lines, tangent planes. These two notions are really the same notion. And I don't know if it's emphasized enough, maybe it was, but if you haven't had that understanding, I want you to have that understanding in this class. But let's do a problem. Let's calculate a little. So let's find a tangent plane. And let's do a, let's use our old knowledge a little bit. Let's find a normal vector. To the graph of f of xy equaling e to the t2y, pardon me, plus sine x at the point phi 0. Find a normal vector to the graph of this guy at this point. What do I mean at this point? I should say at the point. It's the graph, so it's not in 2 dimensions. It's at the point on the graph. Sometimes we'll say over the point. So there are two things I can write. I can talk about the point AB, or I can talk about the point on the graph, and that's just AB, f of AB. All right. So what does it mean, normal vector of a graph? Well, it means it should be normal to the tangent plane of that particular point on the graph. So if I have a normal vector of the tangent plane of the graph, that'll be a normal vector to the graph itself at that point. So really what I'm after is first the tangent plane. We'll say first find the tangent plane, by which I mean find an equation for it. All right, well, we have the equation right here, and the quantities we calculated for the linear approximation are the same quantities we need to calculate now for this function. So we'll need f of pi 0. Well, that's not too hard. That's e to the 2, 0 plus sine of pi, which is not 20, 2 times 0. E to the 0, pardon me, e to the 0 is 1, sine is pi, 0. Great. Now we're going to take the partial derivative of f with respect to x. We can treat the e to the 2y as a constant, goes away, and we're just taking the derivative of sine. So that's just cosine of x. And then we calculate it at our point of interest. It's going to be cosine of pi. Cosine of pi is, say it loud, say it proud, -1. Thank you, guys. I feel so lonely up here. Need help in all kinds of ways. All right, so partial with respect to y, 2 e to the 2y, right? Again, sine of x is treated as a constant, just goes to 0. So take the partial with respect to y, evaluate it at pi 0. I get 2 times e to the 0 is 2. Okay, great. I've got the 3 things I need for either a linear approximation or a tangent plane. Got them all. Now, I just need to put those guys in and get the equation for my tangent plane, which I have right up here. So I'll leave it up. So the equation for tangent plane is the following. This is z equals 1. F of x is -1, so, well, I might as well write -1 times x minus pi plus 2 times y minus 0, so y. Okay, so that's equal to 1 minus, I mean, we can do it, okay, so let's just do it this way. We'll say 1 plus pi. I'll just expand it out a little bit, minus x plus 2. So I'll assemble the constants into one. Okay, good. So what do I do now? What do I need? So I got the equation for a tangent plane. What do I do? Find the coefficients of the x, y, z, right? Find the coefficients of the x, y, z, and I'll get a normal vector, correct? Okay. So x coefficient is -1, y coefficient is 2, z coefficient is 1. Right? Okay, good. Thank you. Very good. Yeah, that's not right. Not correct. Not trying to confuse you. I want you to be alert and astute as these students are. I don't have it in the standard form. I have to put it in the standard form. This expression for the tangent plane is written as an expression illustrating a graph of a function. This is a function of 2 variables, x and y, and we're setting z equal to it. That's a nice way of expressing an equation for a graph of a function. However, it is not our standard form of a plane. The standard form of the plane is that we'll put all of the variables on one side and the number on the other. And so we can bring, I mean, either way, we can, but let's take x and 2y and bring it to the other side. So we'll say x minus 2y plus z equals 1 plus pi. Now I've got the standard form and I can write down the normal vector correctly as the coefficients of x, y, and z. So now I get 1 minus 2, 1. You'll see that that is not a multiple of what I had a moment ago. But it's an accurate normal vector. So this is the answer, or this is an answer. Of course, you can multiply it by non-zero scalar. Questions? Okay. All right, so now we have our notion of linear approximation. We have a way of obtaining an equation for the tangent plane. What's left is this pesky issue of what if it doesn't exist, right? So in one variable, we know that there are some issues. If we took something like y equals the absolute value of x, right? You get this corner point here. And then it doesn't make much sense to talk about the tangent line to that corner point, right? Because you could have a lot of different tangent lines, you know. Doesn't have a single tangent line. So, and that is reflected in the fact that this function is not, the absolute value function is not differentiable at the origin, at 0. So we need a notion of differentiability if we're going to say that a linear approximation is in any way a better approximation, or that we can have a notion of a tangent plane. And that is where the notion of a limit in two variables comes into play. So far, as I said last time, partial derivatives, even in many variables, are defined using only a one variable definition of a limit. So this is the definition of differentiability in two variables. And it's a little hefty, but not quite as bad as the limit definition. All right, so let's suppose our function f of f is defined in an open disk around a point. So there's some point, and we have f defined in an open neighborhood of the point. An open disk. And you can do this in many variables as well, around AB. All right, so we'll say f is differentiable at AB if its partial derivatives are defined there. So f of x, AB, and f of y, AB. These are both defined. In other words, they're limits, so you want to say they exist. And when you look at the linear approximation, you have the following limit. So the limit as xy approaches AB of f of xy, I'll explain this in a moment, minus L of xy over x minus a squared plus y minus b squared, that this equals 0. Where here, of course, L of xy is our linear approximation we had above of f at AB. Okay. So as you'll see, so what are we defining here? We're defining the notion of differentiability of a function. As I said a moment ago, the definition of these partial derivatives involves a one variable limit of a function of one variable. Differentiability requires a notion of a derivative of two variables, or many variables. It needs a limit in that sense. But what is it saying? Well, let's start with trying to break down this fraction. What is the denominator? What is the denominator? Can anyone tell me what the denominator represents? I've got yes. Right, so I've got a point AB. That's the point that I'm asking whether the function is differentiable at. And then I've got some point in a neighborhood, in which let's just think of it as a point in the plane. This denominator is giving us this distance between these 2 points. Okay, it's giving us that distance. Now, what is the numerator? What's the numerator? The numerator is like your error term. This L is a linear approximation to the function you're interested at that point. So this difference is saying how far away the linear approximation is to the actual function. And what this limit is saying as this distance gets close, this does a good job up to a first order of approximating the function itself. Because it's essentially saying that this looks like something times the distance away. It's even better than that. So This is saying that this is a good first, I guess, maybe the way to paraphrase it is, this is a good first order approximation of this. If you're X, a certain amount of distance away, then this will give you an approximation that is something times, better than something times that distance. I don't know, that's a little vague, sorry. But this is the notion. I'll give a picture in a moment to hopefully help with that. In fact, let's do an example. I like this example. It kind of shows how many variables can be more tricky than one variable. So let's look at, well, before I do this, let me just say one thing. So all reasonable functions are differentiable on their domain. I guess I have to say what reasonable means, but I don't want to. So what I mean is, if you have cosine, sine, exponential, log, polynomials, rational functions, so long as you're not dividing by 0, right? These are all nice and differentiable. You can combine them, you can take their powers, you can use composites, so on and so forth. They'll all be differentiable on their domain. Of course, if you see absolute values, you should worry. Right? Absolute values are not very reasonable. And so those are functions where you're going to maybe have some issues. There are also other there are other functions that you might have a problem with. And these would be functions where you see a case definition, where you sort of extend the domain manually. So let me define the following function. So, sorry, I need to make this a little more clear. The xy over the square root of x squared plus y squared, so long as xy is not at the origin. Then at the origin, I'll just take it to be 0. So this is a good example of a function where you would see something surprising in many variables. And where people really do, even people that are, well-trained, make mistakes with these types of things because they forget to ask the question of differentiability. So let's ask, is this function continuous at 0? Sorry, I should say at the origin. Or differentiable at 0. Is it both? Is it one? Here's the problem. All right. Who thinks it's continuous at the origin? Some brave souls raising their hands. I appreciate that. They're only doing this. I can see it. Great. Yeah. Who thinks it's not continuous? Brave. The non-continuous people are much braver. But the non-continuous people are wrong. It is continuous. It is continuous. The limit as x. So now I understand why the people that were going like, it's not continuous, because I talked to you guys about rational functions and how when to suspect the limit doesn't exist. I said, look at the orders. The order of the numerator here is 1 plus 1 is 2. And then I think the people that raised their hands saw the order of the denominator is also 2, because x squared has power 2. However, I'm taking the square root. which lowers it down to 1. So the numerator has sort of order 2, the denominator has order 1. And here you can see that actually the limit as xy approaches the origin is in fact 0, which is the value of the function by order. Definition. So it is continuous, and we can see that in a more formal way by just using polar coordinates and the squeeze theorem. Check using squeeze theorem. Check by squeeze. Just take f of r theta. This is going to be r cosine theta, r sine theta, that's x and y. And then r squared plus sine squared is r squared. Square root is r. This is going to then, we can factor out an r. It's going to be r cosine theta, sine theta. And we see as r approaches r approaches 0, this is bounded. And so the whole thing will have to approach 0. So I won't write the formal argument, but that's the case. Okay, so it is continuous. That's great. So we have a nice continuous function. Beautiful. So is it differentiable? How many think it's differentiable? Nobody. Well, good. It'd be kind of a silly exercise, right? How many think it's differentiable? So when we take the partial derivatives, are we going to get things that are sensible? How many people think that we're going to get something sensible if we take the partial derivatives? Really? Nobody? I can't see. I need to bring my glasses. Okay, good. Some brave soul raised his hand, kind of, and then put it down quickly. Okay. Hey, that brave soul is correct. We are going to get something sensible. This is the thing that I'm trying to explain. Let's take the partial, f of x at the origin. Now, I told you not to do this. I said, don't take the partial and evaluate at the origin. That's true if you're dealing with anything that is reasonable, as I called it up here, although misspelled it. Right? Anything reasonable, you should not do this, but this is not a reasonable function. I've got this weird definition here, which is a case definition. So here, rather than do what you always do, which is use your rules for one variable calculus and take derivatives, you have to use the definition. So I'm going to use the definition of the partial derivative of f with respect to x. And I have to do it at the origin. So I go 0 plus h, 0 minus f of 0, 0 over h. That's the definition of the partial with respect to x, because I'm putting this h in the x coordinate. Let's see what we get. This is the limit as h approaches 0. Now, what is f of 0? By definition, it's 0. So here, this is 0. What is f of 0 plus h? Well, h is non-zero. We're taking the limit as h approaches 0. So this whole thing is non-zero, h0. So we just get this expression with h0, h for x and 0 for y in it. So this is h times 0 over the square root of h squared plus 0 squared, which altogether is 0. 0 minus 0 over h is 0. Take the limit, I get 0. All right? That limit exists, and it's 0. Similarly, I can take the derivative, partial derivative with respect to y, and get a very similar argument. I'll use k here. And you get almost the exact same formula. K approaching 0. Here I'll get 0 times k over square root of 0 squared plus k squared minus 0 over k. But again, all of that is 0. The numerator is 0. Get identically 0 here. Okay. Now, what's going on? I said I agreed with everybody that this is not differentiable, but I just took the partial derivatives. They exist. They're both 0. Well, differentiability is not determined whether the partials exist or not. It's determined by its definition that this limit must be 0. So, let's check this. Well, we have everything we need to write down the linear approximation. It's a super easy one, right? Remember, the linear approximation at 0 in this case is precisely, we'll rewrite it. It's the same as the equation for the tangent line, or tangent plane, pardon me. It's x minus 0, but I get x here, and y minus 0 is y. But it's this guy. Now, in our case, f of the origin is 0. The first partial with respect to x or y is 0. So this whole thing, the linear approximation itself, is the constant 0, which means if we were to have a tangent plane, that tangent plane would just be the xy plane. It would be z equals 0. So now let's look at this limit. Now remember, we don't care, if we're taking a limit, we don't care about the value of the function at the point. So when I write f of xy here, I can use the formula I had above without the special case. So I'll rewrite this. A and b are 0 in this case, so I get the square root of x squared plus y squared. This is the limit as xy approaches the origin. And now, as I said, we know that L of xy is 0 as a function, and f of xy we can write as xy over the square root of x squared plus y squared, because we're not at the origin. And now, all of those that said it wasn't continuous are going to remind me about this limit. I get xy over x squared plus y squared. Does that have a limit? Does it exist? I think we've done it twice in class to show that this does not have a limit. It does not exist. So it's certainly not equal to 0. Certainly not equal to 0. So what's going on, guys? What's going on? Well, what's going on is we can say therefore, which is written this way. Everyone knows that? It means therefore. Therefore, f is not differentiable. Now, what does it mean? So this is what this is the mathematicians saying it's not differentiable, the origin. What's the picture? The picture is this. So this guy is a graph of that function. Now, if you look at the red and the green lines, you'll see that it's constant along the x and the y axis, and it's 0, which means there is no change as you move along the x and the y axis. The first partials are 0 there, right? However, if you are not on the x and y axis and you just tilt it, it looks a lot more like an absolute value profile. Going from different directions, you'll get different tangents. You don't have a tangent plane to this function at origin. Okay. All right, I'll see you guys next week. Have a good weekend.